So let's continue our discussion of the alkanes and turn our minds to constitutional isomers. Of course, we're looking at molecules with the same chemical formula but different structural formulas, which is to say the connectivity of the molecule is unique each time. So looking at pentane C5H12, the simplest isomer is to draw all 5 carbons in a straight sequence. But we can take one of the carbons on the end and stick it onto the main chain as a branch. Now the main chain is just 4 carbons long and would be based on butane, so we would call it 2-methylbutane. Now we might think that we could take this CH3 methyl group and hop it across to carbon number 3, but if we did that, to number the main chain we would now number from the right, and it would still therefore be called 2-methylbutane. So we've got to be careful when we build these molecules and change around the carbons. We need to make sure that we're not just drawing the same molecule backwards or from a different angle. However, we could take one of those carbons on the end and stick it onto carbon number 2 to make a second branch. Now the longest chain of carbons is 3 carbons long, which would make it based on propane, and we'd have 2,2-dimethylpropane. And that's our 3 isomers for pentane. The same chemical formula, but connectivity has been changed, and it therefore gives a unique name each time. And that's one of the easiest ways to recognize whether you have a truly unique constitutional isomer. Can you give that molecule a unique name compared to all the other ones that you've drawn? So let's look at hexane, look at something a bit harder with more constitutional isomers. And we can follow the same rhythm and technique to change the molecule around, switching 1 carbon at a time. So let's take a methyl group on the end and switch it onto carbon number 2 to make it a branch. Now our longest chain of carbons is 5 carbons long, so the name would be based on pentane, and we'd call it 2-methylpentane. We could hop that methyl group across to carbon number 3, and now the molecule would be named 3-methylpentane. Different name, even if it's just a numbering of the branches, so it is a unique constitutional isomer. Now if we tried hopping that methyl group over to carbon number 4, we'd be making that same old mistake again of drawing the same molecule from a different angle. Now we would number the main chain from the right, and this would make it 2-methylpentane again, a molecule that we've already seen. So instead we're going to take another main chain carbon and stick it onto carbon number 2 as a branch. So we've got 2 methyl groups on the same carbon, and we'd call it 2,2-dimethylbutane. Or we could take the methyl branch from carbon number 2, move it across to carbon number 3 to again give us a unique molecule, and it would give us 2,3-dimethylbutane. So there's our 5 possible isomers from hexane. Moving on, let's try something even more challenging. Let's go with 7 carbons for C7H16, and we'll be methodical once more. Take a main chain carbon and turn it into a branch. So now the main chain has 6 carbons. It'd be based on hexane and be called 2-methylhexane. We could hop that methyl branch across to carbon number 3 to make it 3-methylhexane. Now of course we've got to watch out for making the same molecule from different angles. If we drop the methyl group from carbon 3 onto carbon 4, then that methyl group would be numbered from the right hand side and would make it 3-methylhexane again. Exact same molecule, because we've got this mirror image through carbon 3 to carbon 4. So we've got to do something else. We need to take another main chain carbon and stitch it onto the backbone to give us 2 branches. So let's put 2 methyl groups on carbon number 2 to give us 2,2 dimethylpentane. Now of course pentane is the parent chain name because there's only 5 carbons in the main chain, but still 7 in all. We could take one of those methyl branches and hop it across to carbon number 3. That would give us a unique molecule with a unique name, 2,3-dimethylpentane. And then hop the methyl group on carbon number 3 across to carbon number 4, giving us 2,4-dimethylpentane. There's still more things we can do, so let's look at the other examples we can draw. We could take those 2 methyl groups and move them across to the center carbon, carbon number 3, and that would give us 3,3-dimethylpentane, a unique name because of the unique position for the branches. We could also combine those 2 carbons into one branch on carbon number 3, and that would give us 3-ethylpentane. Or we could switch to having 3 branches on the main chain if we steal another carbon from the parent chain, and we'd get 2,2,3-trimethylbutane. That's the last of our constitutional isomers. If we stuck a methyl group onto carbon number 3, then we get lower numbering for the main chain by starting from the right, and it would still be 2,2,3-trimethylbutane. So last one to think about, let's switch to a cyclic compound with cyclohexane, formula C6H12. The formation of the ring has cut the hydrogen count down by 2. Hexane would be C6H14, but whenever we form a ring, the hydrogen count drops by 2. So looking for constitutional isomers of cyclohexane, we'd have to take a carbon from the ring and turn it into a branch. So the main parent chain would go down to 5 carbons with a methyl group coming off, and that would be 1-methylcyclopentane. Some books don't put the 1 in because we've just got 1 branch on the ring. That has to be carbon number 1. So you might see it named as just methylcyclopentane. We could introduce another branch if we reduce the ring size by another carbon, take it down to just 4 for a cyclobutane derivative, and put them on the same carbon to make it a 1,1-dimethylcyclobutane. We could put the 2 methyl groups on different carbons next door to each other, and that would give us 1,2-dimethylcyclobutane. Or switch the second methyl group onto the 3rd carbon to give us 1,3-dimethylcyclobutane. Or combine the 2 carbons to make 1 ethyl branch and make it 1-ethylcyclobutane. But we're not finished yet, we can do more. If we reduce the ring size down to just 3 carbons and use 3 carbons as a branch, first off, we could put 1 branch on 1 carbon and 2 on the other. That would make this carbon number 1 because we get a lower numbering to the branches, and we'd call it 1,1,2-trimethylcyclopropane. We could stick the branches on 3 opposite carbons and give us 1,2,3-trimethylcyclopropane. Or we could put all 3 carbons together to make 1 long branch, and that would give us 1-propylcyclopropane. Or we could make 1 branch twice as long as the other with an ethyl and a methyl branch in a cyclopropane derivative. First example would be 1-ethyl, 2-methylcyclopropane. Or we could put them on the same carbon to give us 1-ethyl, 1-methylcyclopropane. Or we could stick 2 carbons together as a branch and use that last methyl group as a branch on the branch. So the core of the molecule is still 3 carbons in a cycle for cyclopropane. We've got 2 carbons together as a branch, an ethyl branch, And then for the first time we have this branch on a branch. It's attached to the first carbon in the branch, so the proper name would be 1,1-methyl-ethyl cyclopropane. So the parent chain is this cyclic propane, 3 carbons in a ring, and then from carbon number 1 in the ring we've got a branch, but because there's a branch on the branch we need to put everything else inside the parentheses, so we know that this part of the molecule is still coming from carbon number 1, and we name it as if it was a molecule in its own right. It's 2 carbons long, so based on ethane, but it is a branch, so we changed it to ethyl, the YL ending, and it has a branch on carbon number 1, so it's 1-methyl-ethyl, all based on carbon 1 of the cyclopropane.